This is the final video in the EDEXCEL C3 revision tutorial series. Today we will be looking at the final part of organic chemistry and we'll be focusing on esters, fats and soaps. Here we have a popular British sweet, the pear drop, which is flavoured entirely using esters. In this video we will look at the reaction of ethanol and ethanoic acid to produce ethyl ethanoate. We will look at the uses of esters. We will also look at how soap is made and how it removes dirt and grease. And finally we will look at catalytic hydrogenation in order to make margarine. We've looked at esters previously in the C3.11 video on different homologous series. But to recap, esters are compounds with the functional group COO. This is found in the middle of the molecule. Ethyl ethanoate is the main example and is formed when ethanoic acid reacts with an alcohol. So we have ethanoic acid plus ethanol goes to ethyl ethanoate and water. In order to name esters, the part of the ester which has the yle bit comes from the type of alcohol, so ethyl coming from ethanol, and then the anoate bit coming from the ethanoic acid, so the anoate from the carboxylic acid. This reaction is carried out in the presence of a catalyst, and concentrated sulfuric acid tends to be the catalyst that we use. The structural reaction overall looks as follows. So we have ethanoic acid here, and our ethanol going to form our ethyl ethanoate. We can see the COO group here, and finally our water here as well. As we are forming water, this must mean that this is a neutralization reaction. We have our acid, which is our carboxylic acid, in this case ethanoic acid, as well as our base, in this case our ethanol. Ethanol can act as a base due to the OH group, the hydroxide ion that it has as its functional group. This then forms our water as it's a neutralization reaction, as well as our ethyl ethanoate, which is our organic salt. So we have formed a salt plus water. In this case, the ester is our organic salt. We can also represent this equation as a general formula. So our general formula would be an organic acid plus alcohol goes to ester and water. It's also important to note that this is a reversible reaction. So what are the properties and uses of esters? Well, esters are soluble in organic solvents. They also make good solvents themselves. They range from colourless volatile liquids to waxy solids. They all have very strong odours, some of which are very pleasant, and their solubility in water decreases as their chains become longer. Esters can be used to make perfumes due to their strong odours, as well as the fact that they form volatile liquids. This means that they will evaporate easily. Most importantly, esters are non-toxic, which is helpful not only for making them into perfumes, but also for using them as fruit flavourings in cooking ingredients or for uses in cosmetics. Esters can also be used in order to make clothes. This is done by making them into very long chains which contain thousands of esters joined together. This turns them into polyesters. The chains are made into fibres and woven into fabrics. For example, fleece. This means that we can recycle plastic bottles in order to make fleece clothing. As we mentioned on the previous slide, esters have very strong odours, and a large number of these are very pleasant. Depending on the alcohol that we use and the ester that we use, we can make many different fragrances. For example, by combining ethanol and butanoic acid to make the ester ethyl butanoate, we form an ester that smells of apples. Esters are naturally forming organic chemicals and are used by various animals and insects in order to communicate. Bees, for example, make a pheromone known as 3-methyl-but-1-ethanoate, which happens to be the principal component of banana oil. This means that if you were to eat bananas around a beehive, you're going to set off this attack pheromone. We have now looked over the formation and uses of simple esters. However, both fats and oils are also esters and are made from long-chain carboxylic acids. The main difference between a fat and an oil is its melting point, where a fat will be solid at room temperature, whilst an oil will be liquid. Oils and fats are often described as being healthy and unhealthy. For example, you may see people recommending you eat coconut oil, but do not consume vegetable oil. This is to do with whether they are saturated or unsaturated. Saturated means that it contains no carbon double bonds. However, for unsaturated, we can have monounsaturated, so it contains only one carbon double bond, or polyunsaturated, where it contains more than one carbon double bond. As we can see here, we have both healthy and unhealthy oils. Our unhealthy oil is a saturated oil, so it contains no carbon-carbon double bonds, as opposed to our healthy oil, which is unsaturated, so this one will be polyunsaturated, as we have two carbon-carbon double bonds. The number of double bonds that an oil or a fat has affects its melting point. The more double bonds a fat possesses, the lower the melting point is. So therefore oils tend to be unsaturated, as they tend to be liquids, as opposed to fats, which tend to be saturated. Because of this, it can be an issue making margarine spread out of vegetable oil, as the vegetable oil will be a liquid at room temperature, as opposed to where we want it, which is to be a fat at room temperature, be a solid. In order to make our margarine, we need to carry out hydrogenation. To do this, we take a vegetable oil, such as this one here, which is a liquid at room temperature. These oils are made from unsaturated chains of hydrocarbons, as we just looked at, and it is the double bonds between them that keep them a liquid, as they cannot line up neatly enough to form a solid, and the forces between the chains are very weak. In order to make this oil here into a useful cooking product, such as this one here, we need to harden it. This means making the melting point higher so that it's a solid at room temperature. To do this, we need to convert the unsaturated chains into saturated chains. So in order to turn our unsaturated fat, for example here, into a saturated fat, we need to carry out hydrogenation. This is done at 60 degrees C and in the presence of a nickel catalyst. We then bubble our hydrogen gas through our liquid unsaturated fat. This then causes the double bond to break and the hydrogen atoms to be added, forming our saturated fat. This means that the unsaturated fat has been hardened via catalytic hydrogenation. Hydrogenation, as we have added hydrogen, and catalytic due to the fact that we used a nickel catalyst. Hydrogenated oils have a higher melting point and so are solid at room temperature. This means that we can use them for margarines and pastries. We can also use these fats and oils in order to make soap. In order to make our soap from our ester or our oil or fat, we take the oil and we boil it with concentrated alkali solution. The oils then break down into glycerol and long-chain carboxylic acid, so we're breaking them apart. The acids then react with the alkali to make a salt and water. It is this salt that is going to form our soap. This means that most soaps are basically sodium or potassium salts of a very long chain carboxylic acid. We looked over the formation of these salts by the reaction of carboxylic acid and alkali in the previous video C3.10. Now that we have made our soap, we also need to know how it works. Well, soap molecules work by acting like emulsifiers. This means that they have a hydrophobic and a hydrophilic end. The hydrophobic end will dissolve in grease and the hydrophilic end dissolves in water. The hydrophobic end means that this is the end that hates water, so it will go towards the grease, and the hydrophilic end is the part that loves water. Soap molecules, therefore, take on the following look. So we have our hydrophilic end, our hydrophilic head, and our hydrophobic tail. This means that the hydrophobic tails will go into the grease and the hydrophobic end will stick out, surrounding the drop of grease. This then means that the grease can easily be washed away due to the emulsifying action of the soap. So the soap anions surround the oil and form droplets around it, which enables the grease to lift out of the stain. Only the hydrophilic end of the molecule is in the water. This concludes today's video tutorial C3.11 on esters, fats and soaps. And it also concludes the EDEXCEL C3 revision tutorial series.